Today I'm demonstrating installing and running Jinx on an Ubuntu system. We'll start off by installing the Debian package. Jinx is also available as an RPM. After the package is installed, we query the state of Jinx. Jinx informs us that it needs to be reconfigured. What this means is that the Jinx device driver needs to be recompiled and inserted into the running kernel. Jinx acts as a hypervisor under the running operating system in order that it can exactly control thread timings. Installing the kernel module takes about 15 seconds. After the install is complete, we'll extract and compile a sample program, lock-free stack. This sample implements a stack using atomic operations. It has a bug, however. The stack push routine fails to use an atomic operation, and so when conditions align exactly right, the stack becomes corrupted. We start off by running the program under GDB but without Jinx. The bug takes a long time to repro, because on an unjinxed system, the conditions necessary for the bug to manifest are very unlikely. We don't need to recompile our program or change it in any way to run Jinx. All we do is type jinx run gdb lock-free stack, and immediately Jinx becomes a hypervisor under the operating system and starts tracking the GDB process and all of its children. Now the bug happens immediately. We can stop and look around in the debugger, and what we'll see is a typical multi-threaded crash. One thread has crashed, and the other thread, the one that likely caused the problem, has overshot into unrelated code. Jinx provides a better way of understanding this type of situation through its Smart Stop feature. By tracking all communications involved with the bug, Jinx can leave the developer at a place in the debugger that represents the last communication, a place that is likely relevant to the bug. We enable Smart Stop at the command line, and then run GDB again with Jinx. This time, Smart Stop breaks us into the debugger at an intelligent location for all threads. As with the previous example, one of the threads has failed an invariant check, that its item was pushed onto the stack. However, the other thread's location is more meaningful. Here, thread 2 has stopped right after a synchronization. Particularly, it has stopped right after setting the top of the stack, a likely culprit. By looking at the previous executed instruction, we can get an even more direct clue about what happened. By taking the previous executing instruction and asking GDB to show the corresponding line of code, we see that GDB shows us exactly where the bug is, a non-atomic compare and set. Thanks for watching this demonstration of the install and use of Jinx. Learn more at www.forensic.com. Thanks!